Hi everyone. So we're going to start the second part of integration today. And the second part is going to deal a little bit more with the theory around integration and really what it all means. So we're going to start today with a little bit of exploratory stuff so that we can sort of build on an understanding of what integration is really all about. Okay, so let's just start with this. Consider the constant velocity function v equals 30 kilometers per hour, which models the velocity of a car. Okay, so what is the total distance traveled by the car in the first 2 hours? Well, we know that distance is velocity times time. So if we've been going for 2 hours, then distance is going to be 30 kilometers per hour times 2 hours, and unit analysis, the hours cancel, and that gives us 60 kilometers. Okay, so that's how far the car will have traveled in the first 2 hours. Okay. What is the distance traveled by the car in between hours 3 and 8? Well, between hours 3 and 8, that represents 5 hours, right? So time here will be 8 minus 3, which is 5 hours. So distance again is velocity times time, which is in this case 30 times 5, and that's 150 kilometers. Okay, so hopefully so far this is all manageable. Now what we're going to do is graph this velocity function. And this is a constant function, right? So constant function, constant linear function is just a horizontal line. So we've got v of t on the vertical axis and time on the horizontal. Okay, and it's just a horizontal line at 30. There we go. So that's our velocity function, v equals 30. And what we're going to do next, now this might seem a little odd, but we're going to do it anyway, is we're going to consider the area under the curve from time equals 0 to time equals 2. So here's 0, here's 2. And we're going to look at that area. So I'm actually going to just switch colors. And here's the area that we're going to be considering. Okay, so we know that area is length times width. Right, and the length would be the 30, and the width would be the 2, because it's 0 to 2, which is a width of 2. And that gives us an area of 60. Okay, and then we're going to also consider the area under the curve of velocity from time equals 3. So time equals 3 would be like right here, to time equals 8. So time equals 8 is, I don't know, somewhere around here. Okay, so we're looking maybe at this section. Right, that area right there. And this width over here is 5, right? Because 8 minus 3 is 5. So here the area is going to be length times width again, because that's a rectangle, which is the length again is 30, because it's the height, which is the 30, that's the velocity, right? So 30, and then the width is 5. And that gives us an area of 150. Okay. So now what we're going to do is we are going to determine a function for the distance traveled by the car using integration. And we kind of already know what that function is because we've you guys have done a lot of math up to this point, and we know what the function is when we're looking at velocity, time, distance, and the relationship between the three. But let's just formalize that. We know that velocity is the derivative of distance. And so to get distance from velocity, we need to integrate. So d of t is going to be the integral of v of t dt. And that is the integral of 30 dt. And that is 30t plus c. Now at the beginning, we haven't gone anywhere, right? At the beginning, the distance traveled is 0. So d of t is just 30t. And that's since d of 0 equals 0. Okay, so there is our distance function. And now what I want to do is just use that function to again come back to this little exercise that we did with area, and just pay attention to the fact that d of 2 is also 30 times 2, which was the same as our area, which is 60. And let's just see d of 3, d of 3 is 30 times 3, which is 90. And d of 8 is 30 times 8, which is 240. So that means distance traveled between t equals 3 and t equals 8 is 240 minus 90, which is 150, right? And we already knew this because we did this at the beginning. But that also is the same as the area under the curve of velocity, which was the derivative of distance between time equals 3 and time equals 8. Okay, so I just want you to notice that. Keep that in the back of your mind, or maybe at the front of your mind, for a little bit, and we're going to do another example. Okay, so here's another question. We're going to consider a turtle, a very slow-moving animal, that starts at a speed of 0 kilometers per hour and accelerates at a constant rate until it reaches a speed of 12 kilometers per hour over 4 hours. Okay, so that's actually pretty fast for a turtle. But let's draw a graph of this. Okay, so we're looking at velocity and we're looking at time. And now the velocity is changing, but it's accelerating constantly, so it's going to look like this. Here is v of t, and here's t, and here's 0, and then it ends up reaching a velocity of 12. And that happens over 4 hours. Okay, so there's a point there, and it's happening constantly, so this is going to be, or a constant acceleration, I should say. So this is going to be a straight line. As straight as I can make it anyway, okay? So there is our function, a graph of our function, okay? Now, determine a function that models the velocity of the turtle as a function of time. Well, this is a linear function, right? It's linear. For a linear function, we need the slope and the y-intercept. In this case, the slope is like rise over run. So our rise is 12, our run is 4. 12 over 4 is 3. And our y-intercept is 0. So we're going to get that v of t equals y equals mx plus b 3t. Okay, so there's our function. Determine the area under the curve of velocity from under the velocity function from t equals 0 to t equals 4. Okay, so let's just draw this picture one more time. And this time we don't have a rectangle. We're not doing length times width, but we're doing the area of a triangle. So this is 4. This height over here is 12. And we're looking for this area, right? And this, of course, is a right triangle. And the area of a triangle is a half base times height. And so we're doing a half times 4 times 12. So half times 4 is 2. 2 times 12, that's 24. Okay? Now, determine the area under the curve of the velocity as a function of time. Okay, so now we actually want a function for area. So let's think about this. We've got this function where v of t equals 3t. So if we have any point over here, this point is going to be, the x-coordinate will be t, and the y-coordinate will be 3t. Okay, now this is always going to make a triangle. So the area will always be a triangle, which is a half base times height. Okay, the base of the triangle is the x value, which is t. And the height of the triangle is the y value, which is 3t. And that is going to give us a function of a of t equals 3 over 2 t squared. Okay? All right, so there's our area function. Determine the function that models the distance. Okay, now we're getting into distance. Models the distance traveled by the turtle as a function of time, and use this function to determine the total distance traveled by the turtle in the first 4 hours. Okay, well, we know that if we have the velocity and we want the distance, we can integrate velocity because velocity is the derivative of distance. So d of t is the integral of v of t dt, which is the integral of 3t dt. Okay, and that is 3 times a half t squared plus c. And again, because of initial conditions, d of 0 equals 0, we haven't gone anywhere at the start. C equals 0. Okay, so therefore c equals 0. So our function for d of t equals 3 over 2 t squared. And interestingly enough, that is actually exactly the same as what our area function was for the area under the curve of velocity. So let's think about that. The area under the curve of velocity gave us the same function as the integral of velocity. Okay, so I'm just gonna put that out there for a second. Now we also want to find what is the distance traveled by the turtle after for the first 4 hours. So we need to find d of 4, and that of course will be 3 over 4 times, sorry, not 3 over 4, 3 over 2 times 4 squared. And that's 3 over 2 times 16, and that is 24 kilometers. And that, of course, is the same as the area that we got under the curve from t equals 0 to t equals 4, which isn't surprising because, again, the area and the distance have the exact same function. Okay, so now we're going to kind of connect this up. All right, so what connection can we make between the area under the curve of velocity and the distance traveled over the same period? Well, firstly, this is the biggest one. A of t equals d of t. Okay, so on the one hand, area under the curve of velocity is equal to 3 over 2 t squared. Okay. On the other hand, distance, which happens to be the antiderivative or the integral of v of t, is also equal to the same thing. So what can we conclude? We can conclude that the area under the curve of velocity is equal to the antiderivative or the integral of velocity. And that's pretty powerful. Okay, so let's use that in our next example. Okay, the graph below illustrates the velocity of a car in meters per second. Determine the total distance traveled by the car in the first 16 seconds. Now, if we did not know what we had just discovered, we would actually have to write this velocity function out as a piecewise function, integrate each piece, and find the distance traveled over that specific interval and add them all up. That's how we would have to solve this. But now that we know that we can get the same result by just looking at the area under the curve, we can get the distance that way as well. Okay, so that's what we're going to do to make this easier. So we could express as a piecewise function and integrate each part. That would be annoying. Or we can just determine area under the curve. Okay, now the area under the curve from t equals 0 to t equals 16, we're going to have to break this up a little bit because it's made up of different shapes, right? So from here to here we have a triangle. And then, so that's from 0 to 2. And then from 2 to, let's see here, that's 10. We have a rectangle. Okay, and then from 10 to 12, we have this is actually a trapezoid, because a trapezoid is a quadrilateral that has one pair of parallel sides. And then finally, from 12 to 16, we have another rectangle. And we're going to have to basically find the area of each part and add them all up. Okay, so the triangle, the area is 1/2 base times height, which is 1/2. The base here is 2, and the height is 8. And 1/2 times 2 is 1, of course, times 8 is 8. Okay, so that's one thing that we're going to have to add. For the large rectangle, the big rectangle, area is length times width. And our length is, okay, so we go from 2 to 10. So that's a length of 8. And then our width is, oh, that's also 8. So it's actually a square. Oh, well. 8 times 8 is 64. Okay. And then next we have a trapezoid. So the area of a trapezoid is 1/2 a plus b times h, where I'll draw this out for you. So this is what ours looks like. So the height of your triangle, or sorry, your trapezoid is the perpendicular distance between the parallel sides. So this is height. This is A, this is B. Okay, so the area is 1/2 A plus B times H. It's basically an average of the length of the two parallel sides times the height. And we call it height because sometimes both of the non-parallel sides are not perpendicular. In this case, one of them is perpendicular, but sometimes both of them are not. So here we have, in our case, 1/2. Now our A, the longer side is 10, or sorry, not 10, 8. And our B, the shorter side is 4, or you could swap them, it doesn't matter. And then here, from 10 to 12, that's perpendicular height, even though it's sideways, is 2. So times 2. So that 1/2 times 2 makes 1, and then 1 times 8 plus 12 is 12. 8 plus 4, rather, is 12. I'm a step ahead of myself in my head. Okay. And then finally, the small rectangle. Area is length times width again. And our width is from 12 to 16, that's 4. And then our length is, oh, it's also 4. Another square. What do you know? Okay, so our total area is 8 plus 64 plus 12 plus 16, and that's 72, 84, 100. And that means that total distance is 100 meters, because we're looking at a velocity curve, and so area under the curve of velocity is going to be the same as the integral of velocity. Integral of velocity is distance. Okay, and basically that's what I have here in general, right? If a prime equals f of x, the area under the curve is going to be the integral. All right? Okay, so let's make things a little bit more complicated. What if we want to know the area under the curve of a function with nonlinear segments? And what I mean by nonlinear segments is, well, I'll show you on the previous page actually. This graph is made of linear segments because all of the little line segments are straight. And so we can actually break this up into different shapes where we have formulas to calculate their areas. That's not always the case though. So let's look at an example where we can't do that. Okay, determine the area under the curve of the function y equals negative x squared plus 16 from x equals 0 to x equals 4. Okay, so if we think about this function, this is a parabola, and it's the graph of y equals negative x squared, which is like x squared but flipped downwards, and it's been translated up 16 units. So the y-intercept is going to be 16. Whoops, I gotta turn the pen on. Okay, but it's opening downwards, right? And if you think of this function, y equals 16 minus x squared, that's the same as 4 minus x times 4 plus x. So this actually, whoops, has zeros at negative 4 and 4. Okay, so this is what this looks like. Here we go. Okay, and we want to, it's a little wonky, it's not super symmetrical, but you'll have to go with me here. We want to find the area under the curve, and I should say actually bound by the x-axis, between 0 and 4 and the x-axis. And this curve y equals negative x squared plus 16. Okay, now the problem with this is that we can't break it up into triangles and rectangles and squares and trapezoids because it's curved, right? And we don't have like a formula that's going to help us to do so. And so what we can do instead, right, we can't break this into rectangles, squares, triangles, trapezoids, right? We can't do that. What we can do instead is we can approximate the area by breaking it down into rectangles, trapezoids, that sort of thing. And this process is called using Riemann sums because there was a man named Riemann who was the first person to ever do this. And so I'm going to show you what that looks like. And the idea is that we basically break down the interval from 0 to 4 into a bunch of different partitions, okay? So we can, I'm going to do it, I'm going to make things simple and just break it down into 4 partitions, because we're going from 0 to 4. So if we do that, here's 16, here's 0, here's 4. There we go. And the idea is that we're looking at what's the y value here? What's the y value here? What's the y value here? And what's the y value here? And with Riemann sums, we're going to do this by approximating the area with rectangles. And Riemann used a couple of different methods. He used the right endpoint of each partition to approximate. He used the left endpoint, and he also used the midpoint. So we're going to start by using the right endpoint of each partition. And the right endpoint of the first partition is right here. And so this is 16, right? This is basically the point 0, 16. This is the point 1, and then f of 1. Right? So when y equals 16 minus x squared, well, if x is 1, 16 minus 1 squared is 15. This would be 16 minus 2 squared. 2 squared is 4. So this is 2, 4. No, 2, 12, my bad. 16 minus 4 is 12. And then this is 3 over here. So 16 minus 3 squared. 3 squared is 9. 16 minus 9 is 7. And 16 minus 4 squared is 16 minus 16. And so this is the point 4, 0. And so he made these rectangles using the right endpoint. So this would have been the first rectangle. And this would have been the second rectangle. And this would have been the third rectangle. And this would have been the fourth rectangle. Okay, and of course the fourth rectangle has no area. And he said, okay, the area is approximately, well, the width of each of these rectangles is 1. And then the length is whatever the y value is. So the first rectangle has an area of 1, or 15 rather, times 1. And the second one has an area of 12 times 1. And the third one has an area of 7 times 1. And the first one has an area, well, the length of the fourth rectangle is 0. 0 times 1, of course, because it's not actually a rectangle. And so this is approximately 15 plus 12 plus 7 plus 0, right? And so that's 15 plus 12 is 27, plus 4 is 34. Okay, so the area under the curve is approximately 34. Okay, so that's one approximation. And then he said, okay, well, let's also approximate this from the left. And so he drew the same thing. Here's the curve. As we keep going with this, you're going to see my writing gets more and more and more messy. But this time, I'm going to take the left endpoint to make my rectangles. So this is a height of 16. So there's the first one. This is a height of 15. There's the second one. This is the height. This is when x is 2, right? So when x is 2, y is 12. That's the third one. And then this is the fourth one. This is when x is 3. And when x is 3, y is 7. So there's the fourth one. And you can see, you know, just based on these drawings, the right end point is going to underestimate the area or under approximate the area. And the left end point in this case is going to over approximate the area. But the area will be somewhere in the middle. So there we go. And if we do it using the left endpoint, the area is approximately, well, the first one has an area of 16 times, the width here is still 1, plus the second one would be 12 times 1, plus the third one would, or sorry, the second one rather would be 15 times 1, my bad. The third one would be 12 times 1. And the fourth one would be 7 times 1. And that is approximately 16 plus 15 is 31. 31 plus 12 is 43. Plus 7 is 50. Okay? And then he also did it with the midpoint. So now instead of going with the left or the right, we actually find out what is f of 0.5 and go right in the middle, right? So this is going to be a bit annoying, but that's okay. We can do it. Here we go. So here's 0, 4. Actually, I think, well, yeah, okay. I was going to erase this and redraw 1, 2, 3. So we still have these rectangles, but now I want to know what's this point here right in between, right? And what's this point here right in between? What's that y value? Because that's going to make up my next rectangle. And this is going to be even more accurate. What's that? So I'm just going to do this on a calculator. So this is going to be 16. The function is y equals 16 minus x squared. So this would be 16 minus a half squared, minus 0.5 squared, and that happens to be 15.75. Okay, and this is 1.5, right? This is between 1 and 2, so f of 1.5, 16 minus 1.5 squared is 13.75. Okay, and this is between 2 and 3, so this is 2.5. So 16 minus 2.5 squared is 9.75. And then this is between 3 and 4, so that's 3.5. 16 minus 3.5 squared is 3.75. And this is what we're going to use for our areas to try and get it even more accurate. Okay, and so here the area would be approximately, the widths are still 1, of course, 15.75 times 1 plus 13.75 times 1 plus 9.75 times 1 plus 3.75, I got to squish it in, times 1. And that is, I'm just adding it up. It's 43. Right, so you can actually see this one just visually looks the most accurate, and it's fairly in the middle of the method where we use the right endpoint and the left endpoint. So we're doing an approximation here. And then there was one more strategy that was used, which was instead of triangles, we can use trapezoids. So let's just try that. Okay, and to use the trapezoid method, essentially what we do is this. Okay, so I'm going to draw it one more time. This is, oh, actually, I think I do it once more after that. I lied. This is my second to last time of doing this. There's our 16 and 2, 0, 1, 4. No, 3, 4. Okay. So with trapezoids, we make all these points into little trapezoids. So we're going to go like this. And those are what we'll use. The last one, of course, will be a triangle to approximate the area. Okay. So there we go. Okay, and this, of course, is 16, 15, 12, 7, and 0. And remember from before, we did this earlier, that the area of a trapezoid is 1/2 a plus b times h. And because we're multiplying all of them by 1/2, then I'm just going to bring the 1/2 to the outside. And then the a plus b times h, I can do all of that on the inside. So for the first one, the a plus b times h would be 16 plus 15 times 1. And the second one would be 15 plus 12 times 1. And for the third one, it would be 12 plus 7 times 1. And then for the third one, it would be 7 plus 0 times 1. And so all together, that is 1/2 times 31 plus 27 plus 19 plus 7. And that is, let's see, 26 plus 27. I'm getting really tired today. I can't do this in my head. It is 84. And that I can do in my head. That's 42. So these are all like fairly close to one another. Well, at least the last few were fairly close to one another, the last two. And so we can trust that they're probably fairly good approximations. Okay? So now we're going to switch gears a little bit, and we're actually going to integrate this function. Okay? So what is the integral of negative x squared plus 16? Well, that we can do. This will be negative 1 over 3 x cubed plus 16x plus c. Okay? So what is f of 4 minus f of 0? So this might be kind of weird, but just go with me on this. Let's figure out what f of 4 is first. F of 4 is going to be negative 1 over 3 times 4 cubed plus 16 times 4. And that is, 4 cubed is 64. So negative 64 over 3 plus 4 times 16 is 64. And then plus c. Oh, I missed the c, plus c in there, sorry. Plus c, okay? F of 0 is negative a third times 0 plus 16 times 0 plus c, and that's just c. So if I'm doing f of 4 minus f of 0, I'm going to have negative 64 over 3 plus 64 plus c minus c. Okay, so that is, the c's of course will make 0. C minus c is 0. So that's just negative 64 over 3, and then plus 64, I'm going to write that over 3. So 64 times 3 is 192. So plus 192 over 3. And 192 minus 64 is 128. So that's 128 over 3. And that is 126 over 3 is 42. So that's 42 and 2/3. Okay, now that is pretty close to the approximations that we got for area under the curve of the derivative of this function. Because remember what we just did, we integrated and we looked at the antiderivative. Okay, and then we looked at the area underneath. This result is pretty close to that area. Okay, so we're going to bring this all together, I promise. All right. So, area as a limit. This is where we're going to get a little bit more theoretical. Now, what we did with the approximations, with Riemann sum and with the trapezoids, is we tried to approximate area, but it wasn't in fact super accurate, particularly when we did the right hand and the left hand, right? The midpoint and the trapezoids were a bit better, but if we wanted to make this more accurate, we have to think about how we would do that. And the answer is that you've got to make those partitions smaller. You've got to have more partitions, right? So to make the area more accurate, we need to make those rectangles or the trapezoids essentially thinner and have more of them. Okay, so what I'm going to do now is just show you, and this is the last time I promise that I'm going to do this, is I'm going to show you an example of what if we doubled the number of trapezoids? What would happen, right? When we had 4 trapezoids, we got that the area was 42, okay? If we have 8 trapezoids, and the reason why I'm picking 8 is because we already did the midpoint method, so we have all those y values for the 0.5, 1.5, all of that kind of stuff, okay? So if we use 8 trapezoids instead of 4, then as you can imagine, this is going to look a lot more accurate because the little trapezoids are going to be thinner, and so there's going to be less space at the top between, right? We're undershooting a little bit with this trapezoid method. There's a little bit of space at the top, but the thinner we make them, the less space at the top is going to be missing. Right? So essentially what we're going to be doing is this. Here are all our little trapezoids. You can see that this is going to look more and more curve-like the thinner I make those trapezoids, right? And we know these y values. This one's 16, this is 15, this is 12, this is 7, and this is 0. And then we got the ones for the half values over here when we did the midpoint. So those are 15.75, 13.75, 9.75, and 3.75. So I'll fill those in as well. Whoops. So these guys are 15.75, and that's of course the y values, right? 13.75, 9.75, and 3.75. Okay, so that's essentially the height. If we want to know the area, we have to use our trapezoid formula. Now this time, the width of each trapezoid is not 1, the width is a half, but we have twice as many trapezoids. So the area is going to be a half times, well, the first one is 16 plus 15.75 times a half, plus the second one is 15.75 plus 15 times a half, plus 15 plus 13.75 times a half. So this, and then the next one is 13.75 plus 12 times a half. Then I think I'm going to have to go on the next line, plus 12 plus 9.75 times a half, plus 9.75 plus 7 times a half, plus 7 plus 3.75 times a half, plus 3.75 plus 0 times a half. There's my big square bracket. And I actually did this ahead of time because I didn't want to spend a whole bunch of time on my calculator. And this area is under the curve. I should have made this approximately because we're looking at area under the curve, of course. This is approximately 42.5. Okay, so we're getting closer and closer. Okay, now if we kept increasing the number of partitions, let's say we made 16 instead of 8, or 32 instead of 16, or 64, if we kept doubling them, for example, we would get closer and closer and closer, right? So if we increase the number of partitions. Along the x-axis. Right? And what that means is that essentially what we want to do is make the number of partitions infinite, so that each partition is just a tiny, tiny, tiny little sliver, right? These partitions are going to get so skinny that it's like a tiny little piece of paper stacking up against each other, so that these guys along here, there's no gaps at the top, right? And essentially, these now look like line segments, but we want them to essentially model the curve, right? So we essentially want the number of partitions to approach infinity. Okay? The width is going to get really thin, paper thin, even thinner than paper. Right? It'll be a tiny sliver. And the approximate area will actually be the real area. Approximate. The actual area. Okay, that's what we want to do. And that is essentially looking at area as a limit. It's the limit of adding up all of those little partitions, all of those tiny, tiny, tiny rectangles, all of their areas, as the number of partitions approaches infinity. And that will give us the actual area under the curve. Okay, and that brings us to something called the definite integral. Okay, and the definite integral is defined as follows. The integral from a to b of f of x dx is defined as the limit as n approaches infinity of this sum, the sum from I equals 1 to n of f of xi delta x. Now I'm going to draw a picture so that you can see what this delta x, this sum actually means, okay? This sum is essentially this. We're looking, and I'm going to use the same example that we've been using the whole time, at breaking this up into many, 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 many little partitions. So you have to imagine, even though I've drawn them with some width, that they're paper thin. Okay? Now one end is going to be A, and one end is going to be B. And this is going to be, B, right, is going to be equal to the end, xn. A is going to be equal to the beginning, which is basically like x0. This over here would be x1, x2, x3, x4, and then this is the width. And the width is what delta x is. So each of these has a width of delta x. Okay? So essentially what we're doing with this sum is we are summing f of xi. So xi is a plus I times delta x. So that means the number of spaces we've gone plus a. So like if I is 4, then delta x times 4 would be at x4, for example. Okay? Times f of xi, that would be up here. So that's this rectangle, essentially. We're summing that up. Okay? And we're summing up the limit as n approaches infinity, and delta x represents this. It represents b minus a, so this interval divided by n as n approaches infinity. We're making the number of partitions approach infinity. We're making that infinite, making these little segments, or these little partitions, and the width of each partition, which is delta x, paper thin, okay? Now the reason we have to sum them up, by the way, is because we want the area, right? If we just look at one of them, that's just the area of one little tiny sliver. We want the area of the whole thing, so we have to add up all of the tiny slivers, okay? The definite integral is defined as that area. It's the area under this curve, f of x, from A to B. Okay? Now, in fact, you guys may have noticed that the integral symbol actually looks like an S. And it looks like an S because the notation comes from this guy, this letter, which is a sigma, the Greek letter sigma, and that stands for sum. And so the integral is, in fact, a sum of these little slivers of areas. And the integral from A to B of f of x dx is defined as f, capital F of x, from A to B, which is equal to f of b minus f of a. Okay? And that's where f of x is the antiderivative of f of x. Okay, and so we have been working in the first part of integration on finding antiderivatives. And antiderivatives are essentially the areas under the curve of derivative functions. And that's the connection between a derivative and an antiderivative. So I'm going to stop here today. Next class, we are going to pick up a lot more on what all of this means.